Welcome back to the introduction of MEMS. We'll be talking about MEMS wet processing. If ever you see a slanted structure like this in silicon, it's made by wet etching. This is the outline of the entire series. We're at the end of discussing the MEMS process. Silicon is a crystal structure. The silicon wafer that we use have a crystal structure. Typically, a 100 surface is exposed on the front. There are 100 surfaces like this and 111 surface intercepting the XYZ equally, and then 110, which intercept X and Y equally. Wet etching can happen in 3 different ways. If you have a silicon with a mask, you can have anisotropic etching where the etch rate in different crystal plane is different. You can have anisotropic etching that's vertical, or you can have isotropic etching where the etch rate in different orientations are the same. Wet silicon etch is typically conducted in reflux chemical baths like this. A typical reflux system is a glass jar where wafers are placed inside with good circulation. There is a cooled top on top so that the evaporated liquid would drain back into the solution in order not to change the concentration of the solution. You can use EDP or you can use KOH, potassium hydroxide or isolendiamine paracatical. The etch rate is different in different orientations. In the 101 direction, the etch rate is the slowest. This is a wagon wheel structure that demonstrates the etch rate differences in different orientations. 101 is the slowest. As I mentioned, you can use EDP or KOH. It used to be that a lot of people use EDP because the etch rate ratio is very high. But nowadays, people have started to use KOH almost predominantly because EDP is an organic solution that have a very strong smell. So it might be difficult to dispose of environmentally. Now, if you have a 3D structure like this, where the masks are aligned to 110, you're going to form an inverted cavity. The inverted cavity are bound by 4 111 planes. And if you look at the cross section, the slanting degree is 54.7 degrees. The idealized case, of course, is when the etch rate in 111 is exactly 0 or is completely negligible. Then you have 0 undercut. The etch rate is 0 at 111, and the cavity would be bound after forming the inverted pyramid. It will no longer grow any further. That structure is what we call a self-limiting stable profile, SLSP. It's limiting by itself and it's stable. It doesn't matter how long you etch it. Ideally, this is good because in processing you can do over etching and it's not sensitive. You can have transitional profiles that are either unstable or stable. The unstable structures that are transitional changes very rapidly. It's not a good situation if you want to have a high yield process. Depending on the combination of the width of the window and the depth, you can have cavities that look like this, or you can leave a little bit of a silicon at the back. You can have a full inverted pyramid. If the window is very small, then the size of the cavity would be very small as well. Here's one example process where you can use this to make a pressure sensor. You have a silicon substrate, grow oxide on both sides. Use photoresist to pattern the oxide on one side. Oxide is a good resistant to the KOH or EDP etching. And as long as the etching does not completely consume the oxide, you can form a deep enough cavity. Here you don't want to form an inverted pyramid, but you want this to be wide enough that you have a membrane. The membrane depth can be controlled in theory. And after that, you can deposit, for example, polycrystal silicon on the front side, or you might be able to use doping of a piezo resistor. In either case, this is good for making a pressure sensor. Now, however, this is not a very high yield or robust process. What we mean by a robust process? A robust process is one that is not sensitive to over etch or timing error. If you have a process where the result is very much determined by the timing, then you don't have a robust process. In this case, if the etch rate is fixed and you etch a little bit further, then the membrane thickness would change. And that would be not ideal for a pressure sensor device. So only use this as an example. Now, in reality, the etch rating 111 is not completely zero. So what happens is if you have the mask and the edges oriented to 110, when you etch it very short amount of time, then the 111 would be intercepting the mask. But as you keep going further, the 111 starts to have an undercut, and you can actually calculate the amount of the undercut by figuring out the etch rate in the 111 direction. Using this inverted cavity trick, you can create a lot of interesting structures, such as this cavity with a grid on top, or this one, or something like this. Here you can actually see that the cavity has an undercut because this edge appears to be white. It's white because the scanning electron microscope produces electrons that charges the mask, which is non-conductive. Here we have piezo resistors on this side. Or you can create free beams. This is fixed free beams. So this is a very interesting trick. Welcome back to Introduction of MEMS. We will be talking about gas phase etch of silicon. In the extreme case, silicon can be used as a sacrificial layer material. The gases that can etch silicon relatively fast are bromine trifluoride and xenon difluoride. Those two etches silicon without attacking photoresist, silicon oxide, silicon nitride, aluminum, chrome, and titanium nitride. So it is a fairly good material. The only thing that you have to be aware is that you require a special etching chamber because the bromine trifluoride and xenon difluoride, when they react with any moisture in the air, they would form highly concentrated hydrofluoric acid. So it is very important to be safe. Here is a cantilever being etched by a bromine trifluoride after 30 minutes. And then this is after 60 microns of etch. The cantilever is free. You can see that the undercut is quite significant.